Welcome to The Explainer. Today, we're popping the hood on some heavy-duty systems architecture. If you're the kind of person who loves figuring out exactly how massive platforms keep the data flowing without a hitch, you are absolutely in the right place. We're diving into a massive, fundamental shift in the search infrastructure of GitHub Enterprise Server. We'll see exactly how GitHub engineers tore down and completely rebuilt their search architecture for high availability, moving from a tangled, frankly headache-inducing legacy system to a beautifully elegant new solution. But first, let's set the stage with a bit of a nightmare scenario. What actually happens when the core of your enterprise platform starts completely locking up? Just picture it. You're a system admin, and out of nowhere, a routine maintenance check or a minor upgrade completely freezes the core functionality of your entire code repository. Developers can't find their issues, workflows grind to an absolute halt, and your system enters this terrifying locked state that needs super precarious manual repair. The stakes here are literally massive, because on a platform like GitHub, search, it's not just some optional add-on. Okay, let's dive into this. When we say search, we usually just picture a simple little text box at the top of a screen, right? But in GitHub Enterprise Server, search is the absolute bedrock. It powers practically everything. The issues page, the releases page, projects. And yep, even those little notification counts you see next to issues and pull requests, they literally all rely 100% on the search infrastructure. If search breaks, the entire platform just instantly degrades.
Section 1, the clustered architecture trap. Every good engineering story has an antagonist. And for us today, that antagonist is the historical pain point of GitHub's old, incredibly rigid search architecture. Now, to really get why this was a trap, we need to quickly define high availability, or HA. Basically, HA is a setup designed to keep systems running smoothly, even when things fail. In GitHub Enterprise Server, this relies on a classic leader/follower pattern. You've got a primary node, that's the leader, handling all the incoming traffic and writes. And then you have replica nodes, the followers. These are totally read-only, they stay perfectly in sync with the primary, and they're just standing by to take over if the primary ever goes down. This whole pattern is deeply, deeply ingrained in how the server operates. But, well, here was the fundamental problem. GitHub uses Elasticsearch as its search database. And older versions of Elasticsearch, they just couldn't natively support having a primary and a replica node in that strict leader-follower pattern. It literally wasn't built to do that natively at the time. So because of that huge limitation, GitHub's engineering team was basically backed into a corner and forced to make a pretty messy compromise just to get high availability working. That compromise? It was creating one massive, singular Elasticsearch cluster that spanned across both the primary and the replica nodes. Now, at first glance, you might think, okay, that seems fine. I mean, it made data replication straightforward, and it even gave them some performance boosts, since each node could handle search requests locally. But structurally, oh man, it was a total trap just waiting to spring. Which brings us to the ultimate tension point. What happens when a primary shard, the actual piece of the database receiving and validating writes, what happens when that moves to a replica that's just been taken down for maintenance? Well, the entire GitHub Enterprise Server could just end up completely locked up. The replica server would just sit there, waiting for Elasticsearch to say it was healthy before starting up, but Elasticsearch couldn't actually become healthy until that specific replica joined the cluster. It was this brutal catch-22 that absolutely haunted administrators, leaving them with damaged search indexes and some seriously delicate repair steps to get things running again. Look, GitHub engineers are brilliant, right? They weren't just going to accept this. For several software releases, they went on this heroic quest for stability. They threw everything at it. First, they implemented really strict Elasticsearch health checks. Then, they built out these complex drift correction processes just to keep things in line. They even tried building entirely custom search mirroring systems to finally escape that clustered mode. But database replication is incredibly hard. And despite all those heroic efforts, the system still lacked the native consistency it really, really needed.
Section 2, the CCR breakthrough. Thankfully, we don't have to live in that trap forever. After years of wrestling with the old architecture, a native solution finally arrived. A total breakthrough that solved this replication nightmare once and for all. The magic weapon? Something called Cross Cluster Replication. Now, David Tippett, the author of the GitHub engineering blog post we're digging into today, actually anticipated a little pushback here. He jokingly wrote, "But David, you say, that's replication between clusters. How does that help here?" And hey, it's a completely fair question. If clustering across servers caused this whole mess, why on earth is cross cluster replication the fix? And this brilliantly illustrates the whole paradigm shift. In the old architecture, you had one giant, tangled, clustered mode stretching across multiple distinct server nodes. But the new architecture, it completely breaks that apart. Now, each enterprise server instance operates as an entirely independent, single-node Elasticsearch cluster. They aren't tangling their states together anymore. Instead, they're using CCR to communicate cleanly and safely between them. Let's break down the actual technical magic making this possible. Cross Cluster Replication, or CCR, is a native Elasticsearch feature that very carefully controls how index data is shared. It only copies the data after it has been durably persisted to the underlying leucine segments, which, if you're not familiar, is basically Elasticsearch's foundational data store. By natively supporting this leader-follower pattern right at the database level, GitHub admins are never again going to be left in that awful state where critical search data is trapped on a read-only node. Section 3. Engineering under the hood. Now, dropping a brand new database feature into a massive enterprise platform is never just flipping a switch, right? GitHub had to build some serious custom tooling to bridge the gap between Elastic's raw capabilities and the actual reality of enterprise deployments. And the absolute biggest hurdle? The Elasticsearch Autofollow API, which manages this new replication, only applies to indexes created after the replication policy already exists. But think about it, high-availability GitHub Enterprise installations aren't starting from scratch. They are mature systems. They have massive, long-lived data indexes that already exist and desperately need to be migrated to the new system without losing a single issue or pull request. Let's move to and see how this builds into a really clever bootstrapped workflow designed by GitHub's engineers. Step 1. Bootstrap the existing legacy indexes. Step 2. Forcefully attach the new replica followers to those existing indexes. And finally, Step 3. Enable the standard autofollow API so that any future index created just syncs automatically. It's basically building a bridge from the past directly into the future. But that bootstrapping was literally just the beginning. Because Elasticsearch's CCR feature strictly handles document replication, GitHub had to engineer the entire rest of the data lifecycle. They built completely new custom workflows for failover management, safe index deletion, and clean cluster upgrades. They basically took this raw database technology and wrapped a neat, incredibly reliable enterprise bow right around it. Section 4. The upgrade path. So, how do you actually get your hands on this architectural marvel? Let's turn all this theory into immediate, actionable steps for your infrastructure. If you're a GitHub Enterprise Server admin, you can implement this today. Here is your exact playbook. First, shoot an email to support@github.com and tell them you want the new HA setup. Second, download the required license they give you. Third, open up your terminal and run the command geconfigureapp.elasticity.ccr true. And finally, apply that config and upgrade your cluster to version 3.19.1. That's the very first release to support this incredible new setup. So, the crucial point is what happens next. When those servers restart, you really get to witness the magic. The system just automatically untangles the old architecture for you. Depending on the size of your instance, it might take a little time, but the database will automatically consolidate all your data right onto the primary nodes, shatter that dangerous clustering across nodes, and seamlessly restart replication using the brand new CCR method. Now, I want to emphasize one absolutely crucial detail here. 2. That is the number of years until this optional CCR mode becomes the absolute mandatory default for all high-availability GitHub Enterprise servers. GitHub is giving everyone plenty of runway to test this out and provide feedback. But that leaves us with a final, really important question for you to chew on. Are you going to upgrade to the new architecture right now, or are you going to wait? You've seen the risks of the old clustered trap, and you know the elegance and rock-solid stability of the new CCR design. So why spend another month babysitting locked-up servers when the solution is literally just a config change away? Reclaim your time, flip the switch on the new architecture, and let your team get back to building what actually matters. Thanks for hanging out with me on this deep dive. I hope you found this explainer as fascinating as I did.